This is an example for an Excel analysis, and the data are taken from the Pendulum lab from a couple of students who came up with very good results because the Pendulum experiment is a very accurate experiment. Okay, and this is the time that they measured. Here's the length of the pendulum, time in seconds, length in centimeters, and here are the first two data. And then I'm not gonna type everything again, I'm just gonna paste it in here. There we go. I clean this one up just a little bit. There we go. Just align it there. Might just make it look a little better. Alright. With these data, the acceleration due to gravity is determined, so in centimeters per second squared. And here's the algebra. So the pendulum equation is t equals 2 pi square root of L over G, and that needs to be solved for G. So I'm going to square everything and multiply with G, so a couple of algebra steps here in one. And then here's that where I said multiply with G. Okay, this one I'm going to use in a little while, so I'm going to box it in. And now I'm going to divide by t squared. So G equals 4 pi squared L over t squared. And this is what I'm going to use now, and as I said, I'm going to return to the boxed in intermediate step later. 4 pi squared L over t squared. So equals 4 times pi, this is how to write pi in Excel, squared, times L. L is this one here, so I'm going to grab this one here as cell B4, and then divide by the time, which is this one over here. So that is cell A4 squared. Enter, and I'm going to highlight this one here and pull it all the way down on the lower right hand corner. Whoops, yep, there it is. And I come up with a totally wrong result. And the reason that happened is that if you divide just by the t squared, well, that's the time for 20 swings, as the lab explained. That is not the period. So what I would have to do is I have to insert a column which is the time for one complete swing back and forth. And since there are 20 swings, then this one comes out to be the total time for 20 swings divided by 20 swings. There we go. And also pull it down. Looks nice. And now here what I would have to change, I have to grab this cell over here, B4. That looks better. And I'll pull it down, and that looks pretty good. And I'm going to make this look nicer. There we go. This one here perhaps could be considered an outlier. I'm going to leave them in for now. You may want to consider looking at outliers for the data that you get. Okay, I'm going to calculate the average here. So equals average, and that goes from data D4 to D12. There we go. Hit enter, and I come up with an average of 978 centimeters per second squared. So that's just a little bit off, a little bit less than 0.5%. So here I can write average G there we go. Okay, I will do this in a second way by graphing the data. And as I said, I'm going to grab this one here. In fact, maybe I can literally grab it. Oh yeah, there we go. And what I'm going to do is, as I graph these data, I will graph them as a straight line, but I have to do a little bit of a trick here. I have to call this one here X, this one here Y, and when I graph this one as Y and this one as X, I get a straight line with a slope M, and that M here would be readily the acceleration due to gravity, and that's why I wrote it the way I did. So when you do your analysis, look at something similar so that you can graph it as y equals mx, and you can directly read off the slope, which in this case here is the acceleration due to gravity. When I graph these, let's see, there's one, and then I would put here on the y-axis 4 pi squared x, I'm sorry, 4 pi squared L, and on the x-axis I would put t squared, and when I graph these data I come up with something like this here, and then Excel will do a best fit straight line through it, and again the slope of this one here is going to be G, relatively close to 982 centimeters per second squared. As I said, the student data were pretty good. Okay, so that's what I'm going to do in Excel now. Gonna calculate a couple of columns t squared and 4 pi squared times L and graph them. So let's see, t squared, and over here that was 4 pi squared times L. That's just the header for these two columns. So here I'm going to grab cell B4 and square that. Here I'm going to grab 4 pi squared times cell C4. Okay, I'm going to highlight both, pull them down. There we go. Don't need that many digits here. That'll be fine. Maybe one here, one more here. There we go. Okay, and then I graph these data. And it would make sense to put the graphing under data, but in Excel it's under insert. There we go, insert, and then we can see the various way of graphing here. It is always going to be a scatter graph that is not connected, that the dots are not connected. So here we go. Okay, now I have to pull this down a little bit, so actually pull it up a little bit. Okay, gonna go. I don't need that. I don't need these lines here. make it a little bit tighter so we can see more. Okay, so here are the data plotted. And again, this axis here is t squared, this axis here is 4 pi squared times L. In themselves, they don't have much of a meaning, but they just give me the means of coming up with a slope here that will be g as shown in the algebra. I'm going to right click on these data, and down here it says add trend line. I'm going to do that again just to make sure that it's on the video. There it is, right click, add trend line. Okay, here are the options. Linear is what I want. And then display the equation on the chart, display the r squared value on the chart. I'll explain it in a moment. And there we go. In fact, there's my r that I wanted. 978.86 compares to the average, I think it's still here, of 978. So you come up with two results, one from the Excel analysis and one from the average. The r squared value tells us how good the data are. The closer this number is to 1.000, the better the data are. In fact, in physics, it's pretty much unacceptable to have an r squared value below 0.990. So it has to be this good or very close to being this good.